So let's try to remember where we stopped. We did discuss the Poincare duality. For topological manifolds without boundary and compact. Well, let's recall let's recall one of the versions of the Poincare isomorphism. Well, in this isomorphism, well, to begin with, let's say that n is the dimension. What else? R is a ring, and mu is a generator of the top homology group. And we did see some applications in particular. We saw that the Poincare pairing is non-degenerate. And the fact that the Poincare pairing is non-degenerate allows one to calculate the cut product in, for example, in the cohomology of the projective spaces. Well, before we move on to more general versions of the Poincare duality, let's see another application. Namely, the the class of the diagonal and the class of the graph. Well, the class of the diagonal is it's a particular case, but still, let's let's do this this case first. Before before we try to calculate the class of the diagonal, let's recall another thing from the class on Monday. Suppose we have a pair of manifolds which are both orientable, and well, the map is the inclusion map is the inclusion of a submanifold. Smooth, compact, and boundary orientable. Okay, that's I think that's enough. Well, let's denote this inclusion map by I. Well, then I level star of the fundamental class of mu n is the fundamental class of m cap some class, and this class is the Poincare Poincare dual cohomology class of n inside m. Well, we know from the fact that the Poincare isomorphism is an isomorphism that there is such a class, and we denote it dn, and call it the Poincare dual class. Wait, does this make sense?
Yes. Yes.
Okay.
As well.
Well, while we're at it, let's also recall that the transforms intersections, transversal intersections into the cup product of the classes. And there is a sign plus or minus, which depends on one's sign conventions, and basically in most cases we don't really need to know the sign to draw geometric conclusions from this formula. So let's just keep in mind that depending on one's conventions in the CAD product and elsewhere, there may or may not be the sign in this formula. Okay. Let's yes. Let's now focus on the case when the submanifold is the diagonal inside this Cartesian square, and I also make the assumption that R is a field. And then what do I want? I want to calculate the class of the diagonal. Well, how to proceed? Well, since R is a field, we have this isomorphism. The cohomology of the Cartesian square is isomorphic to the tensor square of the cohomology of N. So let's take a homogeneous basis of the cohomology of that. Then we have the dual basis. The Poincare dual basis. What does this mean? Well, this means the roof let me mu and square the cap the roof coup A, and by the way, it's not a square, it's just m. Is delta the roof A, which is 1 if A equals B, and 0 if A is not B. Sorry, and by the way, there's an extra roof, which is not necessary. Let's note this expression by delta AB, although delta BA will be exactly the same thing. So the for general reasons,
I'm sorry, I'm a little bit confused about notation here. That for the Poincare dual basis, for the cup product, why we can have be had cup product with A, shouldn't it be B here to be a cohomology class?
well, since the pairing is non-degenerate for every basis, there's a dual basis. What's written here in in the left-hand side is the pairing of B roof and A. And we if if we have if we have a B a non-degenerate bilinear form then for every basis of for every k basis of V, there's a dual basis, meaning the pairing of an element of the basis with the dual element is 1, and the pairing with the dual of any other element is 0. Does this make sense?
Yes, so what is A here?
Well, A is any element of any element
Okay.
of any element of the basis.
Okay, okay, thanks.
For general reasons, we are able to write something like this: lambda AB A roof cross B. Well, what is A and what is B? A and B are arbitrary elements of the basis B. What are lambda? What are the lambdas? The lambdas are elements of R. What is the cross product? Well, this is a notation we I think we used a few times before. Let's recall it. The cross product can be expressed in terms of the cut product using this formula. Well, so for general reasons, we have this expression for the diagonal class, or in fact for any class, and we need to find the lambdas. And my claim is lambda A B is plus or minus delta AB. And we will calculate the sign and we'll see whether it's plus or minus. Okay. We suppose we have X a cohomology class of some X. Okay, let me put a specific degree here. M X R a homology class of the same degree then X paired with A is an element of R is the result of evaluating of X on A. Basically, we represent X by a cochain and A by a chain, and then we calculate the value of the cochain on the chain. Does this make sense?
Yes.
And this is also equal to epsilon applied to X. A cap X, where epsilon is the co-augmentation map on the zeroth homology, which takes which is induced by the map that takes every single simplex to one. What do we have then? Then we have the following thing. Well, suppose I have A and B, two elements of the basis B, and suppose I want to do the following thing. Suppose I want to take the okay. Let me check what I wrote on the previous page. Okay. So let me let me let me denote the diagonal map by D, and by using notation. Let me denote the image of the diagonal clause by the same by the same letter as the diagonal itself. Okay. Now suppose I take delta and or more precisely, let me take d delta which is the class I'm after. And cup this clause with A cross B, more precisely with A cross B roof, and then evaluate the result on the fundamental on the fundamental. No, sorry, it doesn't make sense. I'll fix it. So we want to evaluate the result on the loss of mu m cross m. Okay, so let's look at this formula again. So this is what we're after. And this is the fundamental class of the square. And the fundamental homology class of the square is what can be taken to be the direct product of the fundamental homology classes of the two copies of that. Now, what does this mean? Well, this means the following thing. The homology since M is a field, the homology oh, sorry, R is a field, M is a manifold. The homology of M squared is the tensor square of the homology of M. And so the image of the tensor square of mu m is a generator of the top homology of m squared, and we denote this generator by mu m cross mu m. So there's a cross product for cohomology, but there's also a cross product for homology, and the notation is the same. Okay. Let's try to rewrite this formula. And what do we get? Well, we get my claim is that we get well, first let me write something, and then we'll figure out the sign. A cross B roof d delta coupe m cross m. Well, let's figure out the sign. Shall we try to figure out the sign? Okay, let me. Oh, sorry. Well, first of all, there's supposed to be a cap instead of a gob. Otherwise, this doesn't make sense. No, still not working. There's a problem here. The product is in the wrong order. It's mu m squared cap d delta. Okay. And it looks to me that no extra sign is necessary in this formula. Wait, what do you think?
Would you please repeat again? I'm sorry.
It looks to me that there is no extra sign necessary in this formula.
But before this,
hold on. There is a sign. When we take mu cap delta d and then cap it with a cross b roof, we get the elements in a different order. So I need to put a sign here, which is something we'll try to keep track of, and the sign is -1 to the degree of a plus the degree of the roof plus the sorry, not plus, all this times the dimension of n. Okay, let me write it in a let me write it like this. And well, in a minute we'll in a couple of minutes we'll see what those signs add up to in the end. Basically, we will write a few formulae, and then at the end we will get delta AB times something, and the something will be plus or minus 1, and we will get an expression for this plus or minus 1. Okay, so what was your question, Lee?
My question here is that for the degree of AB, I believe we need to have some restrictions. Right? They should have the same degree in the homogeneous cohomology ring. Right?
Well, no. Why?
Because we want to have a non-degenerate pairing to produce the dual basis. So
yes, but the dual of an element of a homogeneous element of degree I lives in degree n minus I.
yes, so
and if we have two elements which such that the degrees do not add up to n, we declare the pairing to be 0.
Okay. Mm-hmm.
And with this definition, the pairing is still non-degenerate.
Yeah. Okay. Okay. Thanks. Mm-hmm.
Okay, so let's continue. Now, the result would be epsilon times A cross B roof cross D of the fundamental class of the diagonal. Well, just by definition of by the definition of D delta. Okay. Now, another claim is that the result is epsilon. D upper squared of A cross B roof mu m. And this is the projection formula. Another way to state the projection formula in this setting would be to say that the operator the lower star and the operator the upper star are adjoined to one another with respect to the pairing between homology and cohomology. So the upper star and the lower star are the adjoints of each other with respect to with respect to the pairing on homology and cohomology. Does the formula work? Well, it's almost correct. There's one parenthesis that's missing. Otherwise, it's basically what I've just said. Okay, let me rewrite the formula on the next page. What do I get? I get epsilon then d of the star of a cross roof u. Well, let's see. So, well, epsilon is there, and then we have a cop B roof evaluated on mu m. Well, this follows from the fact that the upper star transforms the cross product into the cup product. Okay, and the result is almost the same as what we get when we when we define the two bases. Namely, we can write B roof A instead of A B roof, but then we get an extra sign -1 to the degree of B roof plus sorry, times the degree of times the degree of A. Okay, now we arrive at this formula. B roof cop A is what we get from this formula, and the result is delta so the result is delta A B. So what has just happened? We multiplied the class we're after by basically by an arbitrary element of the basis, and then we evaluated the result on mu on the fundamental plot. Okay, and what we got was delta AB, with some sign. Okay, well, now well, now we do the same. We do the same for what did we have? What did we have here? We had A cross B roof. Uh, got A prime plus B prime roof. Evaluate on mu m squared. And the result is -1 to the B roof times A prime. A prime B roof B roof prime mu m squared, and the okay, no, this is not the way to proceed. I want to interchange. Okay, I want to put okay, I want to put the roof here. And just the prime here. Then I need to put a roof here. Then I have a prime roof. Here, here the second factor will be the roof cap the prime. Okay. Now, what uh, what does this all mean? Well, I have a cap a prime roof, which is which is -1 a prime roof a, then a prime roof cup a, and so this is the first expression, and then the second expression is just left as it is. Now we need to understand what happens when we take x cross y and evaluate the result on A cross B. And the claim is the result is x A y B with an extra sign again, -1 to the degree of y, degree of A. So the result we have here is the same as -1 to some power times delta A prime, delta B prime, and there is an extra sign, which is which is -1 to okay, I'm lost. I'm lost. I'm lost in science. I'll just write plus and -1. The signs, well, the signs can be recovered from this formula, and the end result. The end result is by comparing these. Let me put an asterisk here. And double asterisk here. By comparing those two results, we get the delta is the sign over B in B -1 simply to the degree of B roof cross B. So the sign of the dual cross the element of the basis itself, and the sign is -1 to the B, and it can be checked. It can be checked by comparing the two formulas. Let's not do this now, or else we'll spend the next hour trying to calculate the sign, which is instructive, but not really worth it. Okay, wait. Any questions?
Just right on this page. For the peak arrow, I didn't get how do we have this equality. From the remark in the middle, I didn't see how to apply the formula in the middle to our original.
Where is the middle?
What?
Which formula you mean? Do you mean by the formula in the middle?
X cross y.
Oh yes.
X cross y and A cross B.
Yes. One. So we also use the fact from the previous page, which says that d mu is the same as mu. So sorry, mu m squared is the same as mu m cross mu m. And then we have a cross of two cohomology classes on the left, and a cross of two homology classes on the right. And
yes,
then,
thank you.
And then we apply this formula. Okay, so this is the diagonal diagonal plus, which we calculated mod some assumptions, and those involve basically the ring, the ground ring being a field, and the manifold is being orientable. Okay, so our next task would be to uh, generalize what we've just done. Suppose we have a continuous map of orientable manifolds. Which are again assumed compact and without boundary. Well, the graph is just a graph. Well, let's recall what this is. It's the set of all x f of x inside M cross N, and we want to let's denote this graph as G of f. Well, there is a map from there is a map I from G of f into to M cross N for the inclusion. And we want to calculate d G of f. The Poincare dual. Well, note the G of the identity map is the same as that. So this question is more general than the one we've just done, and we will see after the break. Let's have a break, and after the break, we will see how to calculate the graph, or more precisely, the Poincare dual of the graph, and then we will see how this implies the Lefschetz fixed point formula. Okay, are there any questions?
So far, no.
Okay, well, in this case, let's have a break and then we'll continue. Now let's save the notes. Okay, let's stop the recording. Okay, so we want to calculate the homology class of the graph of the map, and the idea is after we calculate the homology class of the graph, we can well, assuming the source manifold and the target manifold are the same, we can take the cup product of the two classes with the diagonal, and if it so happens that the cup product is non-zero, then the diagonal must intersect the graph. And what does this mean? This means the map has a fixed point, and which is always a good thing to know. And as we will see, the intersection of the two of the two classes is basically given by the Lefschetz formula, meaning we need to take the alternating sum of the traces of the action in all homology groups, or cohomology groups. Okay, so let's see. So we have a map from M to N, which we assume just continues, and the well the ground ring is again assumed to be a field. Which is a basis a graded basis of the cohomology of M. And we do the same for the cohomology of beta of N. Sorry. And for well, for general reasons, we have the dual class to be is the sum for all d and beta lambda b beta beta b cross beta roof, and the lambdas will be elements of R, and these are the elements we need to find. And the well, the answer will be lambda b beta will be some sign which depends only on the degree of the degrees of the elements involved and on the dimension of the manifold. Let me put. We have two manifolds, so let me put both dimensions. And this all has to be times by the beta b element entry of the matrix of F. Well, F induces a map F prime, sorry, F upper star in cohomology, and since we have bases both in the source and in the target, we can form a matrix, and the idea is that up to sign, what we get is the corresponding element of the matrix. Does this make sense? Wait.
I'm sorry, I got a little bit lost. What the arrow refers to here?
well, the arrow refers to the fact that I've run out of space. And so instead of continuing on the right, I simply put put something on top of the formula, and the arrow means that this thing should go should go together with the formula.
Okay.
And well, it does make sense to consider matrices, and it does make sense to consider matrices of linear maps. And this is exactly what we have here. Does this make sense now?
Yes.
And as for the sign, we will calculate it if we're able to, and if we're not able to, which will probably be the case, I will just state the answer and this will be it. The main thing which is written here is that the sign is the same for all elements of for all beta and b which have the same degree. So the sign does not depend on b and beta individually. It only depends on the degrees of b and beta. Well, we basically proceed as we proceed as in the previous case, but I will just write plus or minus from the start. So let's again take two elements, b and beta, from the respective bases, and we do something similar to what we've just done half an hour ago. recall that we have mu, which is the product of the mu's, the cross product. And we again, the strategy is the same as just half an hour ago. We take the class DGF, which is the class we're after. If we're able to find the pairing of the class, so I will write this down right here. If we're able to pair DGF with an arbitrary element or with all elements of the bases B cross B to the roof of the cohomology of M, sorry, M cross N with R coefficients, then we know dg of F. Wait, does this make sense?
Yes. Yeah, it makes sense to me.
And by the way, I think okay, so in the formula on at the top of the page, we may need to switch the roofs, meaning we may need to take B roof and B roof instead of B, and beta instead of beta roof. Let's look at forget after we evaluate the formula, and then we'll see whether or not we need to make amendments. So I will produce the formula again. Beta cross beta roof, cop DGF, mu. Is this what I wrote here? Yes, it is. Very well. Well, then this is the same as plus or minus B cross beta roof. Mu of the product cap D of the graph. And this is the same as B cross beta roof F lower star of mu m by definition. More precisely by the definition of the GF. And we have this we have a very similar formula. So the next quote is follows from the fact that F lower star and F upper star are the adjoints of one another, and by the way, aside from remark for sheaves, F lower star and F upper star are also adjoints of the adjoints of one another, but in a different sense. For sheaves, these are adjoint functors, and here these are just adjoint linear maps. Very well. What else? Well, we need to calculate the expression we have in the last orbit. So let's calculate it. Well, this thing is the same as Pm upper star of B cup Pn upper star of beta. And if we compose F with Pm, we get the identity.
Pn upper star beta hat.
Oh yeah, sorry. Yes, thank you. If we compose F with Pm, get the identity, and if we compose F with Pn, we get small f. So the result will be simply B cop F upper star of beta roof. Very well. Let's see what if we're able to simplify this expression. Just in case all those plus minuses are the same. Uh, we're basically there, but let's try to understand what the formula means. Well, okay. Let me write this f of beta f upper star of beta roof as the sum of the sum for A in B. Lambda A beta A roof, where the lambda A beta is an element of R. And the result is sum for all A in beta lambda for all A B lambda A comma beta B cap net B cob A roof M. And so this sign is the same as here, but this one will be different. But still, the sign depends only on the degrees. Now let's recall the definition of the pairing. It was on page 1. So we need to take the roof first, and here we have and here the roof comes second. So the result would be plus or minus the sum overall A inside B delta AB. And I've forgotten lambda AB. A beta. Sorry. Blah, blah, blah. Lambda A beta delta AB, which is the same as plus or minus lambda B beta. And these two last signs are the same. In case anyone is interested in the science. And this is basically the expression we have here, which is which is something we get from this formula, and so let's call this formula star. Then we take B prime instead of inside B, beta prime inside beta, and the product of the evaluation of B beta the roof cross cross the roof and is the same as plus or minus.
I'm sorry, but why we want B prime and beta prime here?
Well, I want to I want to pair any two elements which have this form and this basically I have found a pairing of the class DGF with any element of the basis. Now I want to find I want to pair the elements of the basis with themselves with other elements of the basis, and this will allow me to express DGF in terms of the elements of the basis.
Okay. Yeah. Thank you.
So we get plus minus range regular plus minus the I don't know what happened. The roof the cap B roof, the cop B roof cross beta cop beta roof U and percent this and the result is the same as plus or minus B roof cop B evaluated at mu m beta roof cop B beta evaluated at mu n. These are the deltas. Sorry, I've forgotten the primes. No, I'll have to do this over again. Okay, let me take a prime here, and a prime here. Then I have a prime here, and a prime here. And, then I have the primes there as well. And the result is dB B prime and delta beta prime, where I need to replace this with a comma like this. Okay, let me check again if if this is what I need. I think I want to change the roofs. Yes, I need to change the roofs. Okay. Let me change the roofs. Then I need to change them here as well. And it will be beta roof. And then I will have I will have beta roof, cap beta prime, and the result will be exactly the same up to side. Let me call this formula double prime. So the formula of the first formula combined with the second formula implies that the class of the GF is the sum of plus minus now I want to okay, so plus minus and the sum over what? The sum over B in B, beta in beta, lambda B beta, and then I need to put B roof and beta. Sorry, beta B roof cross beta. Where? Plus minus is a sign. It depends only on the degree of beta, degree of B, and the dimensions of the manifolds. And lambda d beta is the B is the beta entry of F in the basis beta roof and B. Okay, so mod some sign issues. The idea is very simple, and it's exactly the same as in the case of the diagonal. Now, do you have any questions?
No, we can proceed.
Very well. So the corollary take m equal n. Then the diagonal and g of f are both inside n squared. Now, what happens when we take the cup product of the dual classes and evaluate the result on mu m squared? Well, the result is again plus or minus the alternating sum, and here we have okay, I will write it in a separate line. plus minus the sum for row I minus 1 to the I, the trace of f upper star on the ith cohomology of M. And this expression is called the Lefschetz number. Of F. And another corollary if the Lefschetz number is non-zero, then f has a fixed point. Which can be further refined if, by saying that if all critical, if all eigenvalues of f are non-degenerate, then or basically different from one, then the if f is smooth and the eigenvalues of df at each fixed point are different from one, then what? Then the Lefschetz number is the number of fixed points with the number of fixed points where each fixed point needs to be taken with sign, and the let's see if we can figure out the sign. I don't remember. I don't remember I don't remember the sign. So let's just leave this ambiguity. Uh, 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 the uh, uh, well, the idea behind this formula has a few generalizations. In particular, there are variants of the Laffer's formula for not necessarily smooth manifolds. For let's just say CW complexes, compact. And also for non-constant coefficients. Etc. etc. There are lots of ways to generalize the Laffer's formula, and as a side remark, the one of the Well conjectures in in algebraic geometry um, uh, is basically a way to calculate the number of points on the number of points over a finite field for a scheme defined over the same field or an extension of the same field, and the signs in algebraic geometry in this particular case are always one. So uh, the Laffer's formula does give one the number of points. And if we take the Frobenius endomorphism as F, and well, it's just one of the conjectures, and there are several more, and these have now been proved by de Ling in the 1970s. Okay, do you have any questions? Wait.
No questions? So let's proceed.
Okay. So let me try to do. Blah, 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 blah. Control. Okay, something happened. Something happened with the board. I need to. I need to get the options bar back. Oh, yeah, there it is. Was easy after all. Just needed to press the right button. The problem is if you press the wrong button, it all disappears, in which case we're in trouble. Okay, so let's see. Well, so far we only discussed the Poincare duality for smooth manifolds or for smooth and topological manifolds, both in the smooth and topological case, but for manifolds without boundary. Now, suppose M is manifold with boundary. Well, let's say that M. Let's assume that M is compact. Compact and connected. By the way, anyhow, that's a compact connected manifold without boundary. No, with boundary. M is orientable. If and if Hn of M mod the boundary is isomorphic to R. Then we define an orientation of an R-orientable manifold in exactly the same way as for manifolds without boundary. Namely, we say that the nth to choose an orientation is the same as to choose a generator of Hn of M, but this time mod the boundary. Suppose dm is is the disjoint union of submanifolds of codimension 0, basically of components. Then we still have the capping with sorry, so wrong. We still have the map from HI M A R to H N minus I M B R. And this map is an isomorphism. And this isomorphism is the Poincare Lafschitz isomorphism. Let's recall that we have the gap product, the relative gap product, HM M A unit B to sorry tensor H I M K to H N minus I M B. This is the relative gap product. And this generalizes the Poincare duality theorem, which we get by setting which we get when A and B are both empty. Okay. Are there any questions?
Would you please give an example that the boundary is a union of some submanifolds of codimension 0?
For example, let's do an example. Let's say car equals Z, M equal the surface of genus 2 minus 2 disks. Well, in this case, we have the boundary which has two components, A and B. Let's call them A and B. And what we have? We have H I of M mod A is isomorphic to H n minus I of M mod B. Well, let's check this.
Yeah, but wait a second here. I'm confused about the codimension of A and B. From my point of view, it should be codimension 1 because above
yes,
it,
codimension 0 where? Codimension 0 in
the bottom line.
In the boundary.
Okay.
I forgot. Yes, I forgot to mention the codimension here is meant to be the codimension in delta M. Well, let's check this example. So what happens when we collapse A? Well, nothing happens except we get nothing in degree 0. So the result of this group will be the group on the top. No, the group on the left will be just Z to Z to some power in degree 1. But which power?
Uh, 2 times 2G4.
Yes. So here we have just Z to the 4 in degree 1. And here we have, well, N is 2. And here we have the same result, Z to the 4 in degree 1. Okay, so nothing happened. But now let's take A equal the whole boundary, B empty. We could do that. We have the same result. H I of M dm. So it's isomorphic to H2 minus I of M mod the empty set, which is the same as H2 minus I M. Well, let's see what this group is. This is the same as the cohomology of M, the reduced cohomology of M with 1. Sorry, not of M, of S2 with 2 points identified. Well, let's calculate the result is the same as hi of S2 wedge S1. And what do we have? We have zero in degree 0. Then in degree 1, what do we have? What's the first reduced homology of S2 wedge S1?
C5.
Yes, it's z to the 4 plus z, which is the same as z5, and then we have z in degree 2. Well, what do we have here? What do we get when we remove 2 disks from S2? Well, in degree 0, we still have z. And in degree 1, what do we have? So we just take m as shown here, which is equal to S2 minus 2 disks. And the result is a wedge of circles, and the question is how many circles do we get in the wedge? What do you think, Wei?
I need some time. I'm sorry.
Well, let's think a little. Let's first take the surface S2 and remove 1 disk. What happens? What happens with the homology?
S2 get reduced homology, so basically, except from degree 0, nothing changed.
So S2 minus the disk. So the 0th homology is still Z, and the first homology is what? What happens if we take a S2 and remove a disk? Just one. For the moment, just one.
Mm-hmm. I don't pick up how to compute it.
Well, there are several ways, and one way would be to represent as 2 as an octagon. Then, if we remove a disk, a small disk in the middle of the octagon, we get a wedge of a wedge of 4 circles. And these correspond to A, B, C, D.
Oh, okay.
And so here we have Z to the 4, and in degree 2 we have nothing, because the wedge of 4 circles does not have anything in degree 4. Okay, so now let's see what happens if I take S2 and remove 2 disks. Well, I still have Z in degree 0, and then in degree 1 I have what? Well, I take the same polygon, the octagon, and I remove another circle. I remove, sorry, not a circle. I remove another disk somewhere else. So the result will be a wedge of 5 S1s. Not 4, but 5 this time. So I get I get Z5 in degree 1 and 0 in degree 2. So the answer is Z5 0. And this is the same answer as the Poincare lattice isomorphism tells us. This Z is isomorphic to this Z, and this Z5 is isomorphic to this Z5. Okay, so the result we get by applying the Poincare lattice duality is the same as we get by hand just by counting how many circles there are in a wedge of circles.
Okay, thank you very much.
You're welcome. Are there any questions, comments, criticism, and so on?
No, but maybe I want to ask about the plan for the Monday, what we are going to talk about.
Well, on Monday, I will see. Well, if I'm able to come up with a comprehensible proof of the Poincare duality or Poincare-Lepschitz duality, I will talk about that. Otherwise, I will talk about something else. The plan is vague so far.
Okay.
Any more questions?
No.
Okay, well, then see you.
Okay, see you on Monday.